So the inclined plane, the start of physics 12, a person is standing on a ramp and they're standing on a Newton scale. What does a scale measure? Think about that. And it's attached to a rope. As the angle of the ramp increases, what happens to the scale reading? A, no change. B, the scale reading increases. C, the scale reading decreases. Once again, this gives us a chance to exercise our democratic right to be heard. So you want to ask yourself, we're on a rope, we're attached to a rope at our waist, and this ramp is getting steeper and steeper and steeper. If I was looking down, what would be happening to the scale? And part of your hint is think about what a scale measures. Who says A, no change? No. Peer pressure there? Who says B, it increases? Who says C, it decreases? Who didn't bother? Oh, okay, sorry, I didn't see the hand there. It's going to come out. All right. So the consensus seems to be that. Convince me. There is a fairly easy way if you see it, and if you don't, I'll be teaching you. You're on the right track. You said 2 key words. The first word was the. The word after that, do you remember? I'm serious. No, not the rope.
Either tension?
No. It was your very last phrase. You said like the, and began with the letter M, then an O, then an R, more. The best way to look at this is look at the 2 worst case scenarios. Flat and vertical. Because it has to continue in a smooth stream between those. And I think I can, because I haven't stood on a ramp before, but I can imagine vertical and I can certainly imagine flat. I've stood on flat. What does a scale measure? Dylan, key idea. What this question really is asking is, what happens to his normal force? You with me so far? Okay. If you're flat, what is the normal force? What have we often said when we've drawn our free body diagram? I've said to you, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. And so far, what has it been? That's the acceleration. mg. Okay? You know what? Let's go like this. Flat. Scale equals mg. Right? Suppose we went dead vertical. Leave a space in the middle, and over here on the right, we'll go vertical. So you're dangling there. If you're dangling there, what's your normal force now? We've drawn that free body diagram a bunch of times too. We had mg down. We had tension up. Did we have a normal force there? So what were we saying? Why didn't we have a normal force? How big was the normal force as a number? 0. Right? Vertical. Scale. And you know what? I'll even go equals Fn so that they know that I clued in that the scale is measuring normal force. Equals 0. So if we go from mg, maximum, to 0, smoothly, are we getting smaller or getting bigger if we end up at 0? What do 3 dots mean? Therefore, decreases in between. By the way, that trick that we just modeled of Akemi looking at extremes, great one to have in the back. So for a lot of these using principles of physics, I'm trying to give you various strategies, and one of mine would certainly be look at the 2 worst case scenarios and assume that it doesn't magically jump back and forth. We're going to assume mathematically it's a smooth curve or a smooth line, or it's smooth. It's not suddenly going increasing, decreasing, increasing, decreasing. It would, if it goes from full to 0, I think it decreases the whole way. We're assuming the universe is orderly. Okay. Example 2. Consider again the person in example 1. As the angle of the ramp increases, what happens to the tension in the rope? A, no change. B, increases. C, decreases. Yeah. You were going to raise your hand with an answer already. You're not even giving us a chance to vote. He likes the dictatorship model as opposed to the democratic model.
I thought we were already in the voting stage.
Oh, okay. Who says A? Who says B? Who says C? Convince me. Psst, I think you can apply a similar argument here. Convince me. Yeah.
On the ground, there's no tension.
In fact, the rope would be slack.
Yeah. And when you're dangling in the air, tension trickles in.
I think we can answer almost the same way, except here we would say tension equals 0. Here we would say tension equals mg in the middle. Therefore, it increases. Here's what I want you to get out of this, Ashcan, my friend. As soon as we're at an angle, don't you dare say the normal force is mg. It's not. It's changing, which means friction is mu times the normal force. That's changing. Oh, that's why the steeper a ramp, the more likely you are to slip off, because friction gets smaller and smaller and smaller and smaller. Why? Because the normal force gets smaller and smaller and smaller, and friction is mu times the normal force. That's why it's harder to stand on something that's steep. Oh yeah, well, there's the physics. I mean, I kind of knew that, but there's the physics behind it. What we really are trying to show you here, Gianluca, is that for objects on a ramp, gravity is doing two things. It's partly pulling the object into the ramp or against the ramp. It's partly creating a normal force, squeezing it on. And it's partly pulling it down the ramp, getting it to slide. Gravity does two things. Gravity does two things. Gravity has two components. Instead of two things, I can use physics terms now. And we're going to be using components. As soon as there's an incline, we're going to say, okay, components. In terms of the other forces, there will be a normal force, but here's the deal. The normal force, look up, don't write this down, is not straight up. The normal force is always 90 degrees to the surface, which means the normal force here would be going up, it's too much of an angle, I can draw better than that. The normal force would be going up about like that, at a slight angle. If the ramp, don't write that down, if the ramp was like this, the normal force would go that way. If the ramp was like this, the normal force would go that way, and it'd be pretty small. If the ramp was like this, well, you'd be dangling in midair, there would be no more normal force. Normal force is going to be perpendicular to the surface. Problem is, gravity is always straight down. So what we're going to do is we're going to break gravity up into its components. It says, draw a force diagram from object on a rough ramp that is sliding. A, down the ramp. B, up the ramp. Okay, let's do down the ramp. What are the forces acting on this block? Get the obvious one. We always have mg, and mg is always acting straight down because that's the way the Earth works. Okay? There is a normal force because it is on a surface. Which way is the normal force? Don't you dare draw it straight up. It's going to be yoink, 90 degrees to the surface, which means it's not the same as mg. Don't you dare say that. Which way is this block sliding in part A?
Right.
Down the ramp. It's not sliding to the right, because the right would be that way. It's not sliding that way. It's sliding that way. So we'll try that again. Which way is the ramp sliding? Down the ramp. Which way would friction be acting then? And you see, by saying it that way, the answer was more obvious, because as soon as I said that, you went down the ramp, up the ramp. Where if we'd done right and left, you might have been tempted to put friction going like this. Yeah. Friction. That way. I'm okay with friction as is because it's nice and parallel to the ramp. I'm okay with the normal force as is because it's perpendicular to the ramp. What we're going to have to do is we're going to have to break gravity up into parallel and perpendicular components. Not vertical and horizontal anymore. We're going to break it up into the part that's pulling it down the ramp and the part that's pushing it into the ramp. Pulling it into the ramp. And what if we're sliding up the ramp? Okay. mg down. Still a normal force. 90 degrees to the ramp. By the way, the word normal in math means perpendicular or 90 degrees. That's why we call it the normal force. We're saying it's always 90 degrees to the surface. Which way is this block sliding? Which way is friction? Yep. No. I was hoping somebody would ask. Graydon said, if it's going up, wouldn't there have to be a force applied? Graydon, my friend, when this leaves my hand on its way up, right there, was there a force applied on its way up? The net acceleration was down, but its initial velocity was up. It's going to slow down and come to a stop. Its initial velocity is up. It's going to slow down and come to a stop, but somebody gave it a big push and then let it go, and it's sliding, and coming to a stop fairly quickly, but sliding, it's going to come to a stop. There is no net force up. Someone gave it a push earlier off the screen and then let go. And we're looking at the after they let go, right? I'm glad you asked, because one of my themes is don't get acceleration and velocity mixed up, right? Don't get net force direction and velocity direction mixed up. Turn the page. Example 4 says, which of the following is the best force diagram for a mass that is at rest? You know what? Let's underline the word at rest. That's fairly important. At rest on a ramp. Explain your answer using principles of physics. Let's come back to this. I think we can answer this question a little bit better by looking at example 5. Here's what we're going to do. And this is one time, Akemi, that I'm going to say to all of you, Sean, wake up, my friend. Is he alive? Give him a kick. Give him a kick. Sebastian, give him a kick. Okay, we're back.
What happened to the earthquake thing?
We had one recently. I don't want to do one. Okay, we're back. Sit up. Sorry. Back here, folks. Look up. This is one time. Look, hey, this is one time I'm going to say to you, I need your attention here. This is one time I'm going to say to you, all of us are going to draw this the same way, and we're going to memorize how to draw this. I'm going to derive the angle tricks once, and then I'm going to say to you, Courtney, do it my way. Okay? I'll show you what I mean. What we're always going to do, Nico, is we are always going to draw gravity straight down. There's mg. And then we're going to draw the perpendicular component. We're going to call this mg. Come on, mg. We're going to call this mg perpendicular. And then we're going to draw the parallel component. We're going to call this mg parallel. I'm using the old geometry symbols for parallel and perpendicular. The symbol for perpendicular is that. The symbol for parallel is that. We're always going to break gravity up into its parallel and perpendicular components, and we're always going to draw perpendicular first. It's this part right here that's pulling the block into the ramp. In fact, that's what the normal force is reacting to. The normal force is the same size as mg perpendicular. And it's this part right here that's pulling the block down the ramp. That's what friction is resisting. Okay? Now, in any one of these diagrams, Brett, you're going to get this angle right here. And what we need to do is find a way to get this angle into this triangle. And my suggestion is we're always going to draw the triangle the same way. You ready? Angle 1 is how big? Yep. How big is angle 2? Whatever theta is minus 90 degrees. You know how I know? Because every triangle adds to 180. And if angle 1 is 90, whatever's left has to add to 90. Theta plus angle 2 add to 90. How big is angle 3? How big is that angle? 3. Turns out anytime you have a Z, these two angles are the same size. We call them alternate interior. Call them alternate interior. So angle 3, how big is it? Same size as angle 2. Which means it's also theta minus 90. You ready? Here's our conclusion now. Look up and watch, see if you can figure this out. How big is this angle right here? 90. How big was this angle, did we just say? How big is that angle? How big does it have to be? (180 minus 90). How big is it? Turns out angle 4 is theta. It always will be. This angle right here will always be this angle right here if you always go perpendicular then parallel. Don't do it the other way. You can, nothing wrong with it, but I just want all our diagrams to look the same. Let's go back for a second. Which of the following is the best force diagram for a mass that is at rest on the ramp? Here's how I would answer this. Here's the mass. What are the forces acting on it? Get the obvious one. Which now I'm going to use a dotted line to break... Oh, that erased. That's not what I wanted. Yeah, that's not what I wanted either. Now I'm going to use a dotted line to break up into mg perpendicular and mg parallel. Put it away. Flip it over. There you go. This right here is exactly the same size as the normal force, because that's what's pulling it onto the ramp. This right here is what's pulling it down the ramp. If these were the only two... I'm going to change colors so I'm consistent. My main forces I've done in blue, haven't I? So let's do that in blue. If those two forces in blue were the only two forces acting on this mass, could it possibly be at rest? No, because I do have these two forces canceling out. Yes? But do I have a force canceling out the parallel component right there? I need one. You said it. The blue forces are your free body diagram. The ones I added in red would not appear on a free body diagram, but when I was solving it, I would resolve gravity into those two components and add them in as dotted lines. It says explain your answer using principles of physics. There's my free body diagram right there. Good enough. Let's start solving some. Example 6. Example 6 says, find the acceleration of a 2 kilogram mass sliding down a frictionless 25-degree ramp. If I said, draw the free body diagram, I would go like this. What are the forces acting on this mass? Get the obvious one. mg. What else? A normal force. And those are the only two forces acting on this. Now, I'm not going to solve this question in this manner. Instead, what I'm going to do is I'm going to add gravity. And if I could give you any bit of advice, it would be make the gravity line fairly long so you can draw a nice big triangle. I'm going to break this up into components. You can use dotted lines. I'll go red. Here is mg, and this is perpendicular to the surface. Here is mg, and this is parallel to the surface. Did they give me the angle of the ramp? You know what? This angle right here is the same as this angle up here, 25 degrees. That's why I went through that little geometric proof for you. Oh, and we need one more force we're missing, the normal force. And do you notice how long I drew it? I drew it the same length as mg perpendicular because they are the same size. And this is why last year you never ever heard me say, oh, normal force is equal to mg. I guess I could have said normal force is equal to mg perpendicular, which is actually going to be true most of the time. Not always, though. Who's winning? Don't say mg, because mg is now out of the equation. It's not even in the same direction as the ramp. I don't even want to look at it. Who's winning? What force is pulling this thing down the ramp? mg parallel. mg parallel. See it? If there was friction, I would have it as a loser. This ramp is frictionless. So mg parallel is winning. I'm going to get this. mg parallel. Any loser? Is there anything up the ramp in the same direction but opposite, in the same line? Let's get tricky with it. Ready? I'm pretty sure mg is the hypotenuse of this triangle because that's the right angle right there. mg parallel, opposite, adjacent, or hypotenuse? Opposite. Which trig function? Sorry, what? I didn't hear you. Sine? Sine of 25 equals opposite over hypotenuse. Get the mg parallel by itself. What am I going to do with the mg on the bottom there? So if I hear you correctly, you're saying the parallel component is mg sine 25. You could memorize that. I don't bother, but you could. I haven't thought of an easy way to remember that mg sine is parallel. It doesn't quite work the way the y thing did. But if you come up with a good acronym, a good way to remember it, go ahead. But I think I can now say this then. mg sine 25 equals ma. Yeah? With me? What happens to the masses? Kind of cool. Turns out it doesn't matter if this is a semi-truck or a small block. It's going to accelerate at the same rate. The mass cancels. And in fact, the acceleration is going to be 9.8 times the sine of 25. Make sure you're in degrees. We haven't done trig for a while, but we're going to be getting tricky with it for the next few lessons. What is the acceleration? Sorry? 4.14. Anybody else? Units? Meters per second squared. Okay, let's do it with friction. Example 7. Example 7. says, consider a 5 kilogram mass sliding down a rough mu equals 0.2, 35-degree ramp. A, find the force of friction on the mass. B, find the acceleration of the mass. You know what we're going to do first? We're going to label our forces. What are the forces acting on this block? Get the obvious one. Gravity. Make it bigger, Mr. Duke. Dope. What else? There's going to be a normal force like that. Which way is this block sliding? So which way is friction acting? Those are the only three forces that are acting on here. If I asked you for the free body diagram, that's what you would write. However, I didn't ask you for the free body diagram, Courtney. I asked you to find the force of friction and the acceleration. To do that, I've got to take gravity and I've got to break it up. I'm going to break it up into a perpendicular and a parallel component. Like that. Oh, and as long as I always go perpendicular first and then parallel, that angle is this angle. It is. It's 35 degrees. What does A want me to find? Friction is what times what? Let's write that down. A, friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force exactly the same size as the normal force, and don't you dare say mg, because it's not. What's the same size as the normal force? Mg perpendicular. So if I hear you correctly, and I think I do, you're saying it's mu mg perpendicular. Let's do some trig. Hypotenuse, still. Adjacent, yes? Which trig function? Cos of 35 equals perpendicular over mg. I think that means that mg perpendicular equals mg cos 35. And that'll work, by the way. The perpendicular is going to be in almost any basic diagram with a slant cos. And the parallel is going to be sine. I usually just draw the triangle and I rederive it, although I'm kind of lazy. I know it's sine or it's cosine. I glance at the triangle, and if it's adjacent, I say, it's cos. If it's opposite, I know it's sine. Yep.
What happens to the mu in that equation?
It's sitting right there. I didn't solve for friction. I solved for the normal force right here, and friction is mu times the normal force. So now we're going to replace this. Friction is going to be still mu, but I'm not going to write mg perpendicular. Zach, what can I write instead? I'm not going to write mg perpendicular, Zach. What can I write instead? What can I write instead? I can replace every single mg perpendicular with a what? No. I can replace every mg perpendicular with a what? Yeah, you do. Help him out, Dylan. I'm not going to, right? What I'm saying is, if these two are interchangeable, drop the mu down, but instead of writing that, go with that. Because that I know. Is that okay? Hey, let's crunch the numbers. Friction is going to be, what was mu? 0.2. What was the mass? 5. G, good old 9.8. Not negative, not positive. We take care of that in our winner minus loser stick. Cos 35. know. Let's see. 0.2 times 5 times 9.8 times cosine of 35. Am I in degrees? I am. You get 8.03. Newtons. What did B want me to find? Acceleration? Cool, I can do that too. Find the acceleration. So let's look back at this diagram here. Which way is this block accelerating? Down. So who's winning? Don't say mg, because it's not. Mg parallel. Who's losing? Is there a loser? Friction in the opposite direction along the slant. Along the slant. Sorry, it's reversed for me. Along the slant. Winner, loser. Here's my equation. Winner minus loser equals MA. Now, we did calculate the force of friction. I know it's 8.03, but I'm going to actually plug in all the variables just so you can see what it looks like. Because friction, we said, was mu mg cos 35, right? Let's go look at parallel. Mg parallel, opposite, adjacent, or hypotenuse? It's opposite. In fact, it's going to be, believe it or not, sine. I can replace Mg parallel, and I'll make a little note here. Mg parallel is Mg sine 35. What that means, Zach, is where I used to see an Mg parallel, I can replace it with an Mg sine 35. Now, what's kind of neat about this? Anybody see it? There is something that appears in everything. What? Turns out the mass cancels. Is there a mass in everything? Who skis? Who skis here? Snowboard, sure. Skier, but skiing is a bit easier. Snowboard, you got a zigzag. Skiing, you can go in a straight line. You skied? Did you ski when you were a little kid?
Yep.
Did you ski with your mom or dad when you were a little kid?
Yep.
Why didn't they have to slow down or speed up to keep you with them? Because the masses cancel. That's why a little kid can ski with an adult. Okay. I don't know if you ever wondered that, but they don't have to slow down, speed up. It's you know what? Without much effort, we're in our magic physics world. There's other things like air resistance that play a role and things like that because a bigger person has a bigger cross-sectional area. But for the most part, this is why a little kid can ski with an adult. Oh, who's been on an amusement park ride before, like the roller coaster? Yeah. Did you have to step on a scale before you got on the ride? Ever wonder why? Masses cancel. If friction is fairly minimal. We'll talk about this in the energy unit too, but it's kind of cool. What's the acceleration? G sine 35 minus mu g cos 35. It's going to be 9.8 sine 35 minus, what was mu, 0.2? 9.8 cos 35. What's this block accelerating down the hill at? .02. Anybody else? People shaking their head.
Why can't we just, because we found friction already, instead of writing it as...
I wanted you just to notice that the masses cancel. I wanted you to see all the variables in their place.
Would it
In fact, you know what? Normally when I do these, I don't bother finding friction first. I go straight to B, and it's a nice clean, oh, the mass is canceled. I went on my little rant about skiing and why little kids can ski with grown-ups. That's why. What do we get? Answer? Is it 4.02? Oh, I thought someone was shaking their head. 4.02? Units? Meters per second squared. Turn the page. Okay, a 7.5 kilogram block remains motionless on a surface that is inclined at an angle of 21 degrees. What is the minimum coefficient of friction on the surface? So now we're asking, okay, what would you need as a mu to keep your traction? Replace the word block with a human being standing with running shoes. How sticky do the running shoes have to be so they don't slip down the hill? Okay. How are we going to start this off? I think we're going to dulp. What did dulp stand for? So I'm going to draw dunk, dunk, dunk. There's my ramp. There's my block. It says the angle is 21 degrees. What are the forces acting on this block? Get the obvious one. Gravity down, absolutely. Normal force. Now, look up, look up, look up. How big is the normal force? It's going to be the same size as my perpendicular component. And if I eyeball the perpendicular component, it's going to be about that long-ish on my diagram. So I can eyeball, normal, it's going to be about that long. You can actually kind of eyeball it ahead of time if you get really good at this. So normal force be about yay big. Because I know those two are in equilibrium. You know how I know? The block isn't sinking into the ramp like quicksand, and it's not flying off into the air like Superman. So I know that the portion of gravity that's keeping it on the ramp has to be the same size as the portion of the ramp that's pushing back. What else? Friction. That's it. If they said draw the free body diagram, that is what I would draw, Kevin. Ah! But they didn't say just draw the free body diagram. In fact, they didn't say draw the free body diagram. They want to know what's the minimum coefficient of friction. Let's break up gravity into its components. Gravity, when we're on a ramp, can be thought of as mg perpendicular and mg parallel, where this angle right here is 90 degrees. Oh, the 21 ends up from here right up in there too. Okay. Who's winning? It's a trick question. It's a tie. It's a tie. So let's call gravity the winner. Let's call friction the loser. But it's going to be winner minus loser equals, if we're motionless, equals what? 0. It's going to be the parallel component, because that's what's pulling us down the ramp, minus friction equals 0. In fact, you know what I could have done if I was really clever, Vlad? I could have said, you know what, just plus the friction over, Mr. Dewick, and you'll get this equation right here. Bunk. They're equal. They're equal. This is why I said, what's the minimum coefficient of friction? Friction could possibly be bigger if necessary. I'm finding out what's the minimum that we need to maintain equilibrium. We could have more, but friction's only as big as it needs to be. Okay. Friction is what times what? I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. So if I hear you right, we're saying mg parallel is going to end up being mu mg perpendicular. you may notice that somewhere along the way our masses once again will cancel, which means actually I didn't need to tell you how heavy this block was. If they hadn't given me a mass and I was a little nervous, Brett, I would have let the mass be 2 kilograms just to play it safe, but I probably would have found that it would have canceled along the way. Let's do the parallel, the left-hand side first. This is hypotenuse, opposite. For parallel, which trig function? This is going to end up being mg sine 21 equals, I'm not done yet, I don't know, mu. I'm doing this all algebraically first, kiddo. We want to look for patterns, see if we spot something. If mg parallel was sine, what was mg perpendicular? Cos. Wait a minute, Mr. Duick. Okay, I'm okay with, I guess, the masses canceled, but Mr. Duick, I'm seeing something else canceled too. What? What the heck does that mean? Okay, it means if you somehow, using a Star Trek teleporter, beamed this onto Mars, the block would still be motionless. Because whatever gravitational field that Mars was exerting would work just fine. You know why? Because it turns out the gravitational field doesn't change the answer. Or if you beamed it to the moon, the gravity on the moon would be enough to hold this motionless. The friction would hold it from sliding down. Or if you beamed it to Jupiter, that would work too. If the G cancels, what that's saying is, doesn't matter whether you're on Earth or any other planet. Which is why I want to do this algebraically, because that is, I mean, it's gnarly cool. Let's get the mu by itself. How would I get the mu by itself? Minus? Plus? Why divide? It's timesing. So you get this. And Vlad, I'm going to pick on you and Nathaniel in just a second. Because I can ask you guys, because you guys did Principles of Math 12 last year. Hey, do you remember? What is sine over cosine? Do you remember?
Tangent.
Ooh. You did Math 12 last year? Yeah. Okay. Okay. For what it's, and I don't memorize this, but for what it's worth, as it turns out, the relationship between it's the tangent of the angle if you want the minimum coefficient of friction. There's one application of tangent, because tangent, it's kind of the weird, I called it the ugly cousin. Anyhow, what's the answer? What is sine 21 divided by cos 21? Sorry? 0.38? Units? None. That's the minimum coefficient of friction. In fact, if your sneakers had that, you'd be uncomfortable because you would feel through your feet that you were almost about to slide. So you'd prefer more, but that's the minimum you need to hold this block in its place.
Gravity can cancel even though, like, no matter where you are, gravity.
Again, what this is saying is this ramp with an angle of 21 degrees, if you had a coefficient of friction of 0.38 on your sneakers, you could stand on this ramp whether the ramp was on Mars or Moon or Earth. The gravitational field is irrelevant. It would still work. Now, you would feel lighter on the Moon. You would feel heavier on Jupiter, but it would still work. We're going to do number 8 at the beginning of next class. For now, you need to practice this. I'm going to say homework. I would like you to try, please. Number 1. Two B. Try number 3.
I remember that.
11. And then we're winding towards the end of this. So from unit review, you can now do number Z. Pause for a second while I get a... Oh, yeah, you can do some of them already, but still. I got 3 more units. Your test is not this week. It probably won't be next week. It'll probably be the week after. So we want to start thinking about review. Number 1 you can do. 2, 3. Could have just said 1 to 3, Mr. Duke. Shut up. For some of them, yeah, I think so. You know what? You can go like this. We can do 1 to 5 is now fair game. Seven, 8, 9, 11, 12, 14, 15, 16, 18, 19. Can do most of these, to be honest. 21, 23, 25, 26. And that's also, so you can start whittling away at those. Try the ones from class today. Tomorrow we're going to finish off this one here. This question here, all we're going to ask is once we find the acceleration, now we can bring in Unit 1 stuff. We can find velocities, we can find distances, we can find times. And then we're also, next class, going to look at some advanced inclines. A couple of nasties. Yes, you may. Hustle back.